Oops.
Okay, we have a few more people in the room and a few more people have joined online. So I guess we can start. The presentation. I would like to thank Akari Asai that was able to find time to join us for our seminar. And it's a great occasion to hear from Akari about her work. I would like to first introduce Akari. So Akari is currently a PhD student in NLP at the Paul G. Allen School of Computer Science and Engineering at the University of Washington. Akari received an IBM fellowship in 2022 and a Nakajima Foundation fellowship in 2019. Her research is centered around natural language processing and machine learning. She's specifically interested in developing NLP systems that are both reliable and adaptable, and with the aim of improving information access. The work that we know of Akari is in the area of general purpose knowledge retrieval systems and models that effectively integrate word knowledge. So this includes her work on adaptive retrieval augmented language models. And we also know her work on multilingual aspects, especially around evaluation. And you know, she has been one of the creators of the XOR QA datasets that some of us have used. So in today's talk, Akari will present on the recent work around task-aware retrieval with instructions. And this work has appeared in the recent ACL 2023 conference as a funding publication. So Akari, thank you again for joining us. We look forward to your presentation.
Yeah, thank you so much for a kind introduction. So today I'm going to mainly talk about our ACL finding paper, but also I'm planning to talk about why we needed to have, so our ACL finding paper is about building a general purpose retrieval system. And today, before talking about the data of the paper, I will talk about why we needed to have retrieval-based system at the first place, and especially what kind of use cases we needed to have a better retrieval system, and how those retrieval system can actually help current state-of-the-art large language model. So large language model have shown to be quite effective in many different NLP tasks, and even in zero shot, they can outperform supervised fine-tuned models. And motivated by such great success of large language model in many different tasks, now those systems are integrated into real-world applications, especially generative data search systems such as Bing Chat, U.com, or Google BERRI. Those systems are quite helpful and useful because now we don't need to search documents by ourselves, and those language model can just search documents for us, and then they summarize the answer, and then write responses in a really easy to understand way. But at the same time, many papers and users report issues of those systems, and we still have a lot of technical challenges we have to solve before actually integrating those systems in such applications with millions or billions of users. One of the biggest issues we have right now is hallucinations, or in other words, large language model can generate factually incorrect responses in a really convincing manner. For example, if I prompt explain Akari Asai, ChatGPT can start generating something convincing, plausible, and the first sentence is actually correct. But even from the second sentence, the model starts generating something factually incorrect. For example, I'm not a research scientist at Google Tokyo or adjunct professor at the University of Tokyo. But the challenge is that the output look kind of plausible and also convincing. So if we don't have prior knowledge or access to external system, it's really hard to know which part is factually incorrect and which part is actually correct. Another issue is that those large language models are trained on massive amount of pre-training corpora, which is collected at certain timestamp. So their knowledge gets outdated pretty quickly. For example, if I ask a question, who is the Prime Minister of Japan, both ChatGPT and GPT-3 generate incorrect answers, saying "yushiki desu ga," but Japanese Prime Minister has been changed in 2021, so those answers are both incorrect. Another big issue we have is more and more papers show that to get factually correct output from large language model, we have to scale up the model size to really massive number of parameters. For example, if we try to get a high performance in knowledge intensive task, then we have to have like hundreds of billions of parameters, which is really expensive, even just for inference. And I believe that those fundamental issues we have in large language models are essentially coming from the same limitation of trying to memorize everything in large language model parameters or parametric memories. So right now, what we are trying to do is we pre-train large language model, and then we try to decode or retrieve their knowledge at inference time by prompting large language model. So right now we are depending on large language models parametric memories, but as I mentioned, this can be easily result in like staleness, knowledge staleness, or scale issue because we have to have a lot of parameters to memorize many different things. And also like usually it's not really easy to memorize everything and then precisely retrieve tiny amount of factual knowledge. So it can be easily resulting in hallucinations. I've been interested in addressing those fundamental issues by leveraging external non-parametric memories. So for example, given a question, who is the Prime Minister of Japan, instead of just prompting large language model, we can find more recent web documents by searching top documents from web, and then like we can incorporate such web document at inference time so that we can avoid those issues. This approach is called retrieval-based language model, and it's getting more and more popular these days and have shown to be quite effective in many different areas. So retrieval-based language model consists of two main components, retrieval model and also language model. And this retrieval component, which is represented as green box here, find helpful document or relevant document from large-scale data store at inference time, and then language model will incorporate these non-parametric memories at inference time by taking this input and also the retrieved document. Those retrieval-based language models, especially this year, are getting more and more paper studies, better architecture, better training, or better prompting method. And if you're interested in, we recently had an ACO tutorial, and you can take a look at the slide from this website. I've been, especially in the past 2 years, I've been working on improving and understanding retrieval-based language model to overcome such fundamental issues we have in large language model. Today, I will focus on the middle part, develop a better general purpose retrieval system. And I will briefly talk about the first one, analyzing the limitation of language model memorization and why retrieval-based language model is quite effective. So for the first part, this is also another paper we presented at ACO. And unlike the second paper, this paper is more on analysis side. And what we are trying to do here is we try to understand the limitation of large language model memorization and why or how retrieval-based language models can help us to overcome such issues. So what we are trying to address here is that the main challenge is we don't know when large language model cannot memorize, and when they are going to hallucinate. For example, if we prompt who is Barack Obama, then many competitive large language model can answer correctly. But if we ask another question, who is Cassie Saltzman's, what is Cassie Saltzman's occupation? And this is another US question. Then like the output is incorrect. But when we started working on this project last summer, there's little work understanding when large language model can memorize and when they're going to hallucinate. So we started working on this issue last year, and we were mainly focusing on factual knowledge memorization in large language model. And so factual knowledge, what we call factual knowledge here is a knowledge triple represented as subject entity, relationship type, and object entity. And we formulate the task as open domain QA, where we transform the knowledge triple into a natural language question, and we prompt the language model with this question, and we check whether the language model output is correct or not. And if the language model can precisely generate this object entity, then we assume that this language model actually memorized this function knowledge. And we focus on 2 dimensions of different factors for memorization. So the first one is whether the subject entity is popular or not, what is measured by Wikipedia page view. And the second aspect is the relationship type, because even if the subject topic is the same entity, some factual knowledge about certain aspect may be harder to be memorized than like other relationship type. And we conduct evaluations across 10 different language models, across 10 different language models from like 4 different language model families. And we found that across those 10 different models, there is a positive correlation between popularity and accuracy, which means that more popular factual knowledge is easily memorized by large language model, while less popular factual knowledge or like long tail knowledge is less memorized. And we have seen more significant correlation in larger models such as GPT-3, O3, or GPT-Neo 20 billion. As a result, we see a positive trend of like performance improvement from smaller model to larger models. And so one natural question is, if the performance or memorization improves as we scale the language models, yeah, maybe like now we have the issue like hallucinations, but as we scale the language model size, maybe we have seen less issues like that. But our analysis shows that this is not true, especially for long tail. So here the red line shows the model performance on more popular entities. And as you can see, once we scale the model size from 1 billion to 175 billion, we can see clear upward trend here. While for the long tail knowledge, what is represented as blue line here, we don't see performance improvement even if we scale model size from 1.3 billion to 175 billion. So we conclude that factual memorization is actually happening as we scale the language models, but usually like large language models only memorize popular factual knowledge. And so the performance or memorization will not be improved in long tail, even if we scale up the model size. So if we cannot improve models memorization in long tail, natural question is like whether we can retrieval-based system can help language model to overcome the limitation of parametric memories. So in this work, we tried a simple baseline, what we call retrieval in context prompting. And this method simply find some top documents from off-the-shelf retrieval systems, such as Contriver or BM25, and we prompt retrieve the document before the original question. So as you can see, it's just like extending the original prompt, and it doesn't require any training or architectural change. But this simple approach actually gives us really large performance improvement across different model size, but especially in smaller model. As a result, retrieval augmented GPT-Neo 1.3 billion can even outperform GPT-3 on this knowledge-intensive task. So why retrieval is that helpful? We found that retrieval-based system show much better performance than the original vanilla language model, especially in long tail. So here the blue box shows the model performance in less popular entities. And as you can see, the retrieval-based language model, which are represented as green and red lines, show much better performance than the vanilla language model, which is represented as a blue line. But another interesting finding here is that in more popular entities, there is much less performance gap between those 2 different paradigms, or actually like the original vanilla language model can even better than the retrieval-based system. Why this happens? We found that, so we did analysis on the record at 1 of the 2 different cases. The first one is the cases where retrieval helps. So language model failed to answer correctly, but retrieval-based language model can answer correctly. The second case, which is represented in the right side, is the cases where retrieval hurts. So language models can answer correctly even without any evidence. But once we prompt language model with retrieved evidence, actually the retrieval-based language models fail to answer correctly. And for those two cases, there's a huge gap in terms of recall at one. And recall at one is a metric to evaluate whether the top one document from retrieval system includes the answer string or not. So these results suggest that retrieval-based language models are quite effective, but right now our retrieval system is far from perfect. And as a result, in many cases, our retrieval system can retrieve unhelpful or even confusing documents, and it confuses our state-of-the-art large language model. So I believe that to build a general purpose, reliable retrieval-based language models, we have to work on improving retrieval side, not only just large language model side. So these findings motivate our main paper today, task-aware retrieval with instructions. And this is a joint work with my amazing professors at Meta, UW, and AI2. And in this work, we try to build instruction following retrieval system that can be used in many different tasks, not only just specific target tasks like question answering. So again, retrieval is essential component in retrieval-based language models, and we have to have a good retrieval system that can be good at retrieving helpful documents for downstream large language models. So here, if we have a query who is the Prime Minister of Japan, then our retrieval system must find this positive document on the top instead of being distracted by other documents that look relevant but don't provide any helpful information to answer this question. In the area of information retrieval, we have seen the great success of neural retrieval system, which is fine-tuned pre-trained encoder systems, usually like fine-tuned on like open domain QA or information retrieval dataset. Those systems have shown to be quite effective when we have enough training data. So here I take the figure from DPL paper, which is one of the most widely used neural retrieval system right now in NLP. And as you can see, if we have many training examples, especially like 40,000 training example, then the performance is much better than BM25, which is a static lexical matching-based retrieval system. But also we can see that the performance gap between BM25 and DPL is somewhat small when we only have 1,000 training data, which is represented as an orange line here. And another paper shows that such DPL or neural retrieval systems, in fact, struggle in zero-shot retrieval context, where we have to train a model on a task, but then we needed to transfer the model to many different tasks without any training data. Here, BM25 is green bar, and DPL is represented as a blue bar. And you can see like there's a huge gap between BM25 and DPL. Well, if we add a neural reranking system, cross-encoder on the top of BM25, we can see performance improvement. Another issue we have in the area of retrieval is that these days we typically try to train separate retrieval systems for different target tasks. For example, given that this like same query, there are many different intents. For example, like we needed to have retrieval system for code search, or retrieval system to find similar questions, or retrieval system to answer these questions, like answer retrieval system to provide answers. But now we formulate the retrieval task as a kind of independent task-specific retrieval adaptation. So we typically have separate retrieval systems for different downstream tasks. But if we want to build a general purpose system like large language model, then like it's really complicated to have a general purpose retrieval system using multiple task-specific retrievers. So in summary, we have two fundamental issues right now in retrieval. The first one is that the model is not really good at zero-shot transfer, and the model is not good at adapting to like diverse users' intents or like align to be like better aligned with users' different needs. And you might think that those issues of retrieval are kind of analogous to large language models, the issues we have in like fine-tuned language model. So prior work shows that, yeah, like we maybe like before 2021, we typically fine-tune large language model for different target tasks, but those models are actually like not really good at like dataset transfer or like new task. But in the area of large language model, what we found in the past 2 years is that once we train a single language model in a diverse instruction and output pair, the model is actually like really good at following the new instructions, dataset transfer, or like generating answers that exactly follow user's intent. So it's inspired by the success of such instruction tuning in large language model. This work, we tried to conduct the first large-scale study of instruction tuning for retrieval. And the end goal of this paper is building an instruction-following task-aware retrieval system that takes diverse query and intents and returns a document that is not only just related to the query, but also follows the instruction, which is similar to large language models. To achieve this goal, we have 3 main contributions. The first one is introducing a new task combination. The second one is introducing a new large-scale instruction-following dataset in retrieval. And the last one is building this like instruction-following retrieval system, which we call TART. And for the first part, we first tried to formulate the task retrieval with instructions and to build a better foundation of, and also like motivate why we needed to have such instruction-following retrieval system. So in normal retrieval, our retrieval system typically takes a query and then return document given the closed domain corpus. While like here in retrieval with instructions, we assume that we only have a single retrieval for different target tasks. And this single retrieval also has access to the diverse open domain knowledge corpus, which consists of like many different documents and many different domains. And this retrieval system takes a query and also instructions that define the user's intents behind this like simple query. And so the retrieval system needs to retrieve document that follows instructions and related to the query. Our second contribution is building a new large-scale instruction-following dataset, because at that time we had several instruction-following datasets, but usually retrieval tasks are excluded from those datasets, such as like prompt stores or natural instructions. So we collected 40 different NLP tasks, including retrieval tasks and also like non-retrieval tasks from 10 different domains, and we convert them into the same unified task format to make the training and inference easier. And as you can see, there are many datasets that are not originally retrieval tasks. And this is because when we only look at retrieval tasks, retrieval task datasets, those datasets mostly like just in 1 or 2 limited domains. Well, we wanted to collect dataset covering diverse domains. So we use the datasets for like legal summarization or like scientific article summarization or like scientific fact-checking dataset. We also annotate on Navier 3.5 instructions for each dataset. And we try to make sure that our instructions are diverse enough. But at the same time, we try to make our instructions cover 3 key components of defining a retrieval task. So the 3 key components are intent, domain, and unit. So intent defines the original user intents or like the end goal of this task, and domain specifies the like target domain or like where the documents should be retrieved from. For example, if a user is not really familiar with the domain, then Wikipedia might be enough. While like if the user is a domain expert, then they might want to retrieve document from, for example, like scientific papers. And so we try to make sure that our instructions for each retrieval task is specific enough to define those different key components, but still have different writing styles. Based on this dataset, we built 2 different retrieval systems built upon the two mostly used architecture in the area of retrieval. So the DPL or like recent like neural retrieval systems are typically like bi-encoder systems that are based on fine-tuned encoders models. So those models, for example, like we take the pre-trained bird model, and then we fine-tune those encoders using existing QA dataset or information retrieval datasets. And once we fine-tune those encoders, then like we encode every single document in the corpus to generate document embeddings offline. And then for each query at test time, we encode a query using the same or like separate query encoder to generate query embeddings. And then we compute similarity between query embeddings and document embedding by computing like simple embedding similarity calculation method. But as you can see, like this bi-encoder method doesn't allow the model to have like bit interaction between query and document encoders. So many recent work shows that it is really helpful if we use additional re-ranking system, which is implemented as cross-encoder on the top of this bi-encoder system. So cross-encoder system, instead of calculating similarity as a like embedding similarities, those systems usually encode query and document jointly using a single encoder, or like sometimes like encoder decoder models or like just encoder models. And then like we get the probability of this document being related to the query. And then we re-rank the document based on this score. As you can see, like it's expensive because now we have to jointly encode query and document, so we cannot compute offline. So it is not scalable to like millions of documents. So we typically combine like these bi-encoder systems and cross-encoder system to build the best retrieval pipeline. So here we prepend the original annotated instructions to the original query. For example, like retrieve a Wikipedia article that answers the following question, and then like we add the query. And then we use exactly the same bi-encoder architecture or cross-encoder architecture. One challenge here is that, so one important thing is to train bi-encoder or like cross-encoder system. The most important thing is having the good positive and negative document, because typically for training, we use those positive and negative samples to train dual encoder system using contrastive loss, or like using those example for using standard crossing entropy loss. And many papers show that if we don't have a good negative or positive samples, usually the model performance is not optimal. So in this work, we explore different approaches of creating hard negative, creating negative documents. And especially like I would like to talk about instruction unfollowing negative, which is first introduced by our work. So the hard negative document, which is a kind of middle part, is a negative document that are following instruction, but not exactly answering to the query. For example, like here, the hard negative document, the green box shows that which Python function can I use to compute square root, to the query, which say how to compute square root in iOS. So both two questions are coming from Stack Overflow. So this document actually satisfies the instruction saying like retrieve a question asked in Stack Overflow. But when we actually look at the questions, then like this Stack Overflow question about Python function is not exactly the same as the iOS square root function, so it shouldn't be considered as as positive. Another type of negative sample is instruction unfollowing negative. So here, this orange box shows the a Stack Overflow answer, which actually like talk about the Objective-C or Swift square root function to implement the square root in iOS. So if we only look at the query, this paragraph actually answers the question. But again, the task instruction here is retrieve a question that is similar to this query. So we shouldn't retrieve answer. So this this negative document is actually related to the query, but it doesn't follow the instruction. And we combine those two different hello negative samples in addition to the original paragraph documents provided in our dataset. And we trained the model, the TART dual model, which is based on bioencoder, and also the cross-encoder based TART full model on our dataset using our new negative sampling strategy. And we evaluate our model on two setups. The first one is zero-shot retrieval evaluation, where we train our systems on one or like multiple dataset, but we evaluate the models on output domain datasets. And there are two major datasets that are popular for this zero-shot retrieval evaluation. Another setup which we newly introduced is cross-task, cross-domain evaluation. So in this BEIR or like LOTTE setup, typically like we have query and also we have closed domain corpus. So for example, like for Quora duplicated question retrieval task, we have Quora questions and our knowledge corpus is close to Quora questions. But in real world applications, we have open domain or like our knowledge corpus can include many different documents from many different sources. It can be from like Wikipedia, or it can be from community question site, community QA sites like Quora or Stack Exchange, or it can be even from like scientific papers. So we believe that like this zero-shot retrieval is the important and helpful task, but it's not really realistic in terms of like those end applications. So that's why we decided to try this new setup, cross-task, cross-domain evaluations, where we combine different queries and document corpus from 6 different tasks, and we mix all of the knowledge corpus into a single retrieval target. So, and as you can see, when we just look at the query, sometimes the intent behind this query is not really obvious. So our model, the models needs to take the additional implicit instruction, user instruction into consideration when it comes to retrieval. So if the task is retrieving similar question, and if the model just retrieve answer, then the model will be penalized. And for both setup, our task-aware retrieval system, TART-4, which is based on cross-encoder, shows significant performance improvement from contributor or contributor plus normal cross-encoder. This shows effectiveness of instruction tuning, and I will talk about more detailed analysis result later. But at the same time, we noticed that the task-aware retrieval system based on bioencoder architecture only doesn't give big performance improvement from the baseline contributor. And we have two hypotheses for this limited improvement. The first one is that for bioencoder, we typically cannot scale up the model size to like billions of parameters. And many papers show that to make instruction tuning work, we actually needed to have really big base models. And the second reason is that, as I mentioned, in bioencoder architecture, we don't have that much rich interaction between query and document, or query plus instruction and document. So we assume that it's actually like really challenging for the model to learn to precisely locate instruction plus query embeddings to be closer to the target documents just from our normal training. So I think it is important to explore like better, more efficient architecture of instruction following retrieval, because cross-encoder is expensive, but it's also really helpful to understand why achieving instruction following by encoder is more challenging than instruction following redundancy model. And we found that more helpful instructions give much better performance than like unhelpful instruction or like no instructions. And also removing instruction at training or test time gives us significant performance drop on like all zero-shot evaluation benchmark and also cross-task, cross-domain evaluation benchmark. So we believe that instruction is actually helpful for this cross-encoder based instruction following retrieval system. Lastly, we found that our negative samples is actually important to make the model to learn to follow instruction and also retrieve more helpful document. So here the green box shows green bars show the performance without any negative example, any hard negative example, but have some like more kind of more simple negative example. And the green box shows the blue box shows the model performance without instruction unfollowing example. And as you can see, removing instruction unfollowing example causes large performance drop on cross-task cross-domain retrieval, because for this task, we have to precisely understand instruction and retrieve documents that are not only just related, but also following instruction. And removing hard negative samples causes large performance drop on zero-shot retrieval task as well. Before talking about the conclusion, I would like to briefly introduce some related and concurrent work. So this work was released right after our TART paper, and the work is trying to build a better embedding method using instruction tuning method. So, and they evaluate the model performance on many different evaluation tasks, such as text evaluation, classification, clustering, but they also test on retrieval tasks. And the experimental results show that instruction tuning is quite effective to get large performance improvement for classification, summarization, or entailment tasks. But they also found that it is hard to achieve performance improvement on retrieval tasks by doing instruction tuning for embedding-based method. So here, embedding-based method is a by-encoder method. So I think this is still an open question. And I think this finding is similar to our finding, and it is still open question on how to build by-encoder-based instruction following retrieval system. Another paper which uses large language model and instruction in another, in different way from our work, is a prompt getter from Google. So in this work, they use large language models and also use task-specific instructions. But instead of directly using instruction as a part of input at test time, they use instructions on large language model to generate training data for customized retrieval system. So for example, there are 5 different target tasks, downstream tasks, and they prompt large language model, which is 175 billion plan model, using instructions and also 8 future samples. And then they generate millions of training data and train task-specific retrieval and reranking models using this task-specific training data. And they show that this their model shows much significant performance improvement from zero-shot transfer, which is only using MS Marco during training time. And this work is somewhat related to our work in that both of us are using large language models and task-specific instructions for retrieval. But the main difference is that in our work, we try to build a single retrieval system by using instruction tuning at training time. Well, in this work, they try to train task-specific or customized retrieval systems by using large language model generated training data. And I think the area, the intersection between large language model and retrieval is a really exciting area. And many people are trying to use such large models for reranking or generating more training data, or trying to build a better instruction following retrieval system based on our work. So in summary, in this paper, we introduced a new task formulation, retrieval with instructions, to shift information retrieval paradigm from multiple task-specific models to a single unified task retrieval, where user can flexibly interact to get the related and also related documents that satisfy their information needs. And we construct the first large-scale instruction tuning dataset for retrieval tasks by combining 40 different NLP tasks and unify them into a same instruction, query, and positive and negative sample format. And based on this dataset, we built a task-aware retrieval system using 2 different architectures, and we showed a strong zero-shot and open cross-task, cross-domain performance. So today I talked about 2 papers, and mostly the second paper And we've been also working on improving language model component as well to make language models better at integrating those non-parametric memories with their own parametric memories. And if you're interested in, I list all of the previous publication on my website. And those two papers I talked about today are listed at the right bottom side. And I'm happy to take any questions. And if you have more technical questions, feel free to send email to me.
Thank you very much, Akari, for the talk. So I would like to open the floor to questions. So we have a few people here in the room and a few people online. If you have a question, just for those online, just unmute yourself and fire off the question. Let's start from people here. Anyone?
Yeah, I do have a question.
Okay, Shinyo.
Yeah, so you have used a lot of different instructions for different domain, and like pure data set, BEIR benchmark, basically. I also tried a similar thing, but for me, I was like manually, as you have like domain, the intent, this kind of unit, but you still need to kind of manually create a prompt for each different. So my question is there any like more systematic way to do this instruction prompt for your target data set?
Yeah. What I've been interested in is automatically generate instructions given the input query and also the expected positive paragraph and negative paragraph. Because I think in large language model, some people explored ways to generate instructions given like expected input output pair, or like even like just different combination of like humanitarian small number of input output examples. But we haven't seen that kind of work in information retrieval area. And I'm actually like really interested in like how effective those like generating instructions or query itself from like large language model, given like small amount of like demonstrations. Excuse me.
Yeah. Good. Dylan?
Yeah, hi. It's a very good talk. I'm just wondering, for the retrieval and generation pipeline, that's somewhat different to the previous retrieval only or ranking pipeline that we use in ECG, for example, for evaluation. Now you have and generation. Do you think that the retrieval part still stay the same as previous method, or like for example, for the two passages that you retrieve, it should be somewhat different from each other, that we, for example, consider the diversity as well, that can be also fit into the generation, that might be more valuable. Can you elaborate more about this?
Yeah, I think many like common or like simple approach are just like using existing retrieval systems that are trained independently from like large language model. But also some recent papers show that it is actually quite helpful to train language model and retrieval end-to-end manner, because the type of like effective paragraphs from the like end performance aspect is actually like different from like those better performance evaluated on like retrieval, like for example, like recall at 5 or like recall at 10 metric. So I think one interesting thing is like whether like we have a better training paradigm to build a better retrieval-based language model, and the best retrieval system for retrieval-based language model may be different from like the best system for like retrieval as an end task. And the second thing is another interesting line of research is integrating retrieval in more kind of like having a better integration between retrieval and language model. Like for example, like just retrieving like end phrase or like tokens using like retrieval model only without having any language model, or like still like having two components but sharing encoder and like integrate retrieval document in like hidden layer space something. But compared to like just using retrieval model as a part of like independent pipeline, those areas are not fully explored. So I'm kind of want to see like more work in like those like training and like better architecture area.
Yeah. So I have a question, a comment that is related to these, and also is related to the premise of your talk. Is related, I believe, to the thing we see in this slide where you say improving generation with better control, and is related to a panel we had on generative AI last week at SIGA-IR. So my comment and then question are these. We are believing that retrieval augmented language models are kind of the silver bullet against hallucinations, right? And we have done a small scale study. When small scale, I mean a limited set of topics, like about 50 topics on a very specific data set, health and misinformation. We got one language model, GPT 3.5, and what we did was we manipulated the input that we were passing as evidence, as retrieval augmentation to the language model, right? And we manipulate it across different dimensions. One of them being relevance, another being correctness, right? And what we saw is that if you give the perfect passage in terms of relevance, correctness to the language model, that doesn't necessarily address your hallucinations, right? And so there is this struggle between model knowledge and evidence knowledge, augmentation knowledge. And so I believe you have done some work recently at how can we better control the language model generation phase using effectively this evidence. I wonder if you can comment briefly on that and give us pointers of that work here.
Yeah. So right now we are working on 2 different projects, hoping we can archive sometime soon. But I can briefly talk about what we are working on right now to have better control, especially the issue of hallucination. So the first one is that so many recent papers combine retrieval system with a large language model trained independently from retrieval, such as GPT 3.5. And I believe it is not optimal because those language models are not trained with such retrievable document, and they're not trained to learn to incorporate retrievable document or learn to ignore those unhelpful document. So that can sometimes this result in knowledge conflict between non-parametric memories and parametric memories, or something large language model can be easily distracted by such unhelpful document. So one project we have is training a language model with retrieval component, but instead of just adding retrieval document in input, we make language model to judge whether this retrieval document is actually helpful and how it should use using special feedback during training time. And we found that this enables us to control how much information we should use from retrievable document, or how often we should retrieve to overcome the issues such as hallucination. And we found that this is quite effective to control language model output. And another thing is that we try to build a system that can detect hallucination and fix the errors in a post-hoc manner. So our task setup is given a language model generated text, our another pipeline system, which consists of retrieval and language model, can take those erroneous language model generations, and we kind of post-edit errors given retrievable document. And also we provide fine-grained error type and also the edits to remove these factual errors. And we found that actually training retrieval-based language model for this specific downstream task is actually important to have better control. Well, if we only use off-the-shelf retrieval system plus GPT-3, we still we don't have good control. And now we have a good small enough language model, not small, but Llama 7 billion, 13 billion, which even academia can train. So I think it is still important to train a retrieval-based language model, but in a better way, just beyond prompting large language model API. And I hope we can release a paper sometime soon, but still working on it.
Yeah, thank you. That's very insightful. There are a few questions online, so I read them for you. They are in the chat. The first question is from Rui Hong, and there has been a follow-up already on that question. So Rui Hong says, well, thank you for the talk. He says, I have a question about how retrieval assists the language model performance. In the early slides, the help from retrieval to language model is smaller when the language model is larger. So, for large language model, retrieval gives little improvements in effectiveness, right? And the question, so he says, and the experiment is just extended to GPT-3. So I think he means it's just on GPT-3. What about larger language models?
So yeah, on the top of GPT-3 or ChatGPT, still like retrieval-based approaches give us performance improvement. And we haven't tested GPT-4, but at least for like ChatGPT, retrieval is helpful if we, in two different ways. The first one is retrieval-based prompting, and we found that even just adding retrieval context in ChatGPT prompt, it gives us large performance improvement. And for the second, our ongoing project, we actually evaluate and improve ChatGPT, retrieval-augmented ChatGPT output using our hallucination detection and editing models. And this model can actually help us to identify and fix the errors from such large language models. And I think even with such like GPT, ChatGPT, or GPT-4, those models are definitely getting much better than like original GPT-3 or 2 or like vanilla or 3. But still we see performance, we still see issues of hallucination, especially like when we look at the query or input about long tail entities. And so at this point, yes, it's still helpful. But yeah, we might not see like that performance gain, or like we don't see like that hallucination in GPT-5. But yeah, if we don't have any hallucinations, maybe like I will be excited. So
So follow up to that question is that in these initial slides, you were showing that when the large language model was getting the answer incorrect, and you were doing retrieval, then you improve accuracy. And sometimes the large language model was doing correctly without retrieval, and then the additional retrieval produced an incorrect answer. So the question is whether it's possible, or you see it's possible, to optimize at test time whether incorporate retrieval or not. So almost have a flexible path that can automatically detect when retrieval is needed, and target that, start that pipeline.
Yeah, it's a great question. So actually, I didn't talk about that part in this talk, but in this paper, we have a really simple approach that decide when not to retrieve and when to retrieve. So what we did in this work is we just, we have a simple pipeline with retrieval-based language model and just like language model. And we decide whether we should use retrieval or not based on how popular the subject entity is. And this adaptive retrieval method gives us large performance improvement on the top of GPT-3, because on GPT-3, the base language models are pretty good, while like our retrieval system can even confuse language model. So if the base model is not really strong, for example, GPT 1.3 billion, retrieval is almost always helpful. But for in case of GPT-3, we found that we only needed to retrieve 60% of the time, while like for the remaining 40% of the time, just like we can use the standard language model and still we can get the correct answer. And I think this type of adaptive retrieval approach is quite important, especially like in the era of strong large language model. And my current project is actually trying to build a language model that can decide when not to retrieve or like when to retrieve while generating. Yeah, I'm really excited about this adaptive retrieval-based language model.
Yeah, thank you. So before we go to another question that there is in the chat, I wonder if somebody else here in the room or online has a question. I don't see anyone raising their hands, not here. So, okay, let's go to another Rui Hong questions that is in the chat. So he was asking whether DSI, that is differential search index, can be integrated with large language models. And so I think what he means here is that, yeah, of course, you know, DSIs can be used as a retrieval approach for your retrieval augmentation. But I think what Rui Hong here is wondering is whether one could use DSI not to generate the document ID, so not to generate the ranking, the retrieval part, but actually even to generate an answer, right? So again, going towards the idea of having an end-to-end pipeline that does the search and the generation, right? And so I think what he's saying, and he's confirming is, you know, could DSI be one of these architectures that is end-to-end?
Yeah, let me, sorry, yeah, I might misunderstand the terminology, but my understanding of DSI is a like method which generate like retrieval document from like language model instead of retrieving document. So it's kind of like a generative search system.
It generates document ID, right? So,
So we have the baseline here. So GenBeat, I think it's a type of like one of the like DSI method published at BEIR this year. So this method prompts language model to generate evidence document and then like use this evidence document for inference time. And in our adaptation, we prompt, for example, GPT-3 to generate evidence and then use this evidence for like the final answer generation pipeline. And we found that this GenRead actually shows exactly the same weakness of large language model. So here the GenRead is like orange line here. And you can see that like those two models, vanilla language model and GenRead based language model pipeline, shows much worse performance than retrieval based model for like long tail. And I think this fundamental limitation is similar to the vanilla language model. So vanilla language model is good at memorizing and retrieving fact about popular entities, while they still struggle in long tail. So I think the generative search method or DSI is quite interesting and exciting area. But I think it's still important to note that those models may exhibit exactly the same limitation as the existing large language models, such as hallucination and staleness, where the parametric, non-parametric memory retrieval method can help to overcome.
Thank you for that. Yeah, Rui Hong was happy with the explanation. Any other last-minute question, burning question, comments? I personally am excited to see what will happen once we use large language models to generate data scale, and we publish this data, online. So imagine content creators using large language model, and then we grounding our search and our QA systems on data that has been generated by large language model. That would be really exciting time. Sorry, that was a bit of a pessimistic view of the world. Okay, Akari, thank you very much again for
thank you so much.
It was a pleasure to have you here, and it was great to hear about your work. And we hope to get in touch again soon for further comments and follow-ups and ideas.
Sounds good.
We can again.
Feel free to send emails if you have any questions. And thank you so much for inviting and great questions. Have a great day.
Thank you. And have a good night. A good evening.
Thank you so much.
Bye bye. Thank you. Bye.